if a tree falls in the forest and no one's around to hear it, does it make a sound? Everyone's heard this question, and everyone has their own answers. None could really be proven right or wrong until maybe now, with quantum mechanics, which is the study of subatomic particles. They actually may have stumbled upon the answer. So today I want to talk to you guys about the double slit experiment. It's one of the most amazing and mind-blowing experiments in modern day physics. And I've always been very interested in mysteries in science fiction. And when I read about it, I realized it was one of the best mysteries in science non-fiction stories I've ever read. First I want to talk about some basics, then I want to jump into the experiment and finally come to the conclusion. Before we begin, I want to talk about John Wheeler. He was a theoretical physicist who worked with Albert Einstein and Niels Bohr. And he once said, if you're not completely confused by quantum mechanics, you do not understand it. So, for this presentation, my goal is to completely confuse you. But before I do that, we've got to go over some basics. First, what's a particle? Particles make up you, me, everything we see. They have mass, and they are basically atoms. And what's a wave? A wave, think sound wave, radio wave, it's a transfer of energy. The best is to think of dropping a stone in a pond and the ripples that proceed out of it. So let's look at some common sense experiments. If I have 100 green soccer balls covered in wet paint in front of me, and in front of that is a black canvas, and between us is a sheet of metal with one slit. If I kick these balls at this slit, I'm not that good at soccer, so I'm not going to go through every time, but the times I do go through, it's going to have a pattern on the canvas like this, where the soccer balls hit. Now if I take that metal sheet, put it in water, drop a stone behind it so the waves ripple out, hits this, then when they hit the back wall, which let's say measures the intensity of the wave, you'll have a wave intensity something like this where it's centered in the middle where the slit is. Alright, now if we do the same thing with two slits, obviously the canvas is going to have two streaks where the balls go through. Now if we do it with waves, it's a little different because the waves are going to come out and there's going to be two waves at each slit, and which causes something called wave interference. Here are two waves. If they're in phase, meaning the tops meet and the bottoms meet, then they sum and add together. So if it's like you're at an ocean, two waves come over each other, it's usually a bigger wave. Now if they're out of phase, meaning a high meets a low, the second wave, and a low meets a high, they sum together to zero. They just cancel each other out. And here's just a short animation. Here's the two slits and the waves coming out. And as you can see, there's these patterns right here where it's cancellation, there's no waves, but then there's highs and lows everywhere else. So the back wall of intensity looks something like this, where the whites are the intense patterns where it's either high or low, and the blacks are the cancellation. That's wave interference pattern. Okay, so here's Louis de Broglie. He is a French theoretical physicist, and in 1923 he was writing a thesis paper on, and his thesis topic was he wanted to figure out if maybe electrons could possibly be waves and not particles. Now everyone thought he was crazy because electrons have mass. They're like tiny soccer balls. They're obviously particles. That's what everyone said. And like any good scientist, he decided to do the experiments anyways. And so let's look at the experiments. This is an electron gun. It shoots tiny, tiny electrons. They're like tiny, tiny, tiny soccer balls. They have mass. Now, he shot it at a double slit, just like we did with soccer balls. And instead of a canvas, he used a photoelectric paper that picks up on the electrons. So, what everyone expected him to get was a particle pattern, such as this. It looks like the soccer balls that went through the slits. But what he got was wave interference. So everyone said, okay, it's because you're shooting a stream of electrons, they're bouncing off each other, interfering with each other. So he agreed, and he did the experiment again, shooting them one at a time. And looked at the photoelectric paper, and again, it was wave interference. This confused all scientists, because the electron has to pass through one slit, just like a soccer ball, and so it can't interfere with anything except for maybe itself. So the idea was that somehow the electron was passing through both slits at the same time, causing wave interference. It's interfering with itself, which is very weird because it's being in two places at once. So they thought this was crazy. They have to do some more experiments. So they put sensors on each side of the slits and a computer that monitored what went through the slits, and every time a particle would pass, it would calculate it, count it, and they did this to figure out if there's anything funky going on, like the particle somehow went through both slits at the same time, which isn't really possible. So that's why they did it. So when they ran the experiment, looked at the photoelectric paper on the back wall, they got a particle pattern. They'd been getting wave patterns all this time, and now they want to figure out what's going on, and they get a particle pattern. And the particles only went through one slit at a time, nothing funky. So they did many experiments, and one of them that they later did was they cut the wire between the computer and the sensor. So the sensor's still on, they're still flashing when a particle goes through, but there's no way to really check which slit the particle went through, the electron. And when they did this, they got a wave pattern. So now they don't know which slit the electron went through. So what they thought was the act of observing actually changed the outcome because they know what's going on. By knowing which slit, what path it took, somehow changes the outcome on the photoelectric paper. Okay, so that's really confusing. But they decided to do more experiments, and one was the delayed quantum eraser. And it's the same as the other setup with the computer connected, but this one has an erase and show button. So what this would be is they do the experiment, they don't look at the data's hidden on this computer, and then an hour or so after the experiment's run and finished, they either show it or erase it. So they show the data, see which slit the electrons went through, or for each one, and then they look at the photoelectric paper, or they erase the data, then look at the photoelectric paper. This is to determine if the act of observing does have some effect. So they did this, the first time they did it, they showed it. They wanted to see the data, see that there's something funky going on, all of that, along with the electrons, and they got a particle pattern. So they're like, okay, let's do it again. They wait a day after they run the experiment, they erase the data, and they get a waveform. They don't know where these particles are coming from, how they're interfering with itself. So this came up with they came up with the Copenhagen interpretation, which is that there's no information on the back wall of the photoelectric paper until we choose to look at it, meaning that the particles don't actually land until we choose to look at it. It can be different depending on the information we have at the time. It's really weird and confusing. But remember, these are soccer balls. These are particles. They have mass. These are electrons. But they did this experiment in 1999 with carbon structures, 60 atom big carbon structures, which are huge compared to an electron. Same outcome. So I hope you're at least a little confused about the double slit experiment, or I did not do quantum mechanics justice. And if you ever get a chance to ask a theoretical physicist if a tree falls in the woods, does it make a sound and goes around, they'll probably tell you no, because remember, the act of observing actually changes the outcome. And this is quantum weirdness.